Hello, bachon. So, today we're going to tackle a very important topic from our current electricity unit, Kirchhoff's rules. Now, I know the name sounds a bit intimidating, but don't you worry. We are going to make this so simple that you'll never be scared of it again, and you'll get full marks in the exam, for sure.
All right, so this is our roadmap for today. We're going to go through it step by step so that everything becomes absolutely crystal clear. Let's begin.
So, first things first, let's try to understand why we even need these new rules. I mean, we already have our good old friend Ohm's law, right? V equals IR. So what's the need for something new?
Just take a look at this circuit. See, there are so many cells, so many resistors, all connected in this, complicated way. Now, if you try to find the current in each wire using only V equals IR, well, it's going to be very difficult. Go ahead, try to find a simple series or parallel combination here. You'll see, you'll get stuck pretty quickly. And this is exactly where we need a more powerful tool, a proper method to solve these kinds of complicated circuits. And guess what? That is precisely what Kirchhoff's rules give us. You can think of them as like a special toolkit for a circuit detective. Okay, so let's pick up our first tool from the toolkit. It's Kirchhoff's first rule, also called the junction rule. And I promise you, this one it's super simple and makes perfect sense.
To understand this, just imagine some water pipes meeting at a point. The total water flowing in must equal the total water flowing out. Simple, no? Water can't just vanish or get stored up at the joining point. Well, what's really cool is that electric current behaves in exactly the same way. Nothing is lost at the junction. So here's the official NCERT definition, and this is what you should write in your exams. It says that at any junction, the sum of the currents entering the junction is equal to the sum of the currents leaving the junction. It's saying the exact same thing as our water pipe analogy. And why is this true? It's based on a very fundamental principle, the conservation of charge. Charge cannot just accumulate at a junction. It can't get created or destroyed there. So whatever comes in must go out. And this picture here illustrates the rule beautifully. Just look at junction A. You can clearly see that current I3 is coming in, and at the junction, it splits into two currents, I1 and I2, which are going out. So the rule is simple. Incoming current I3 must be equal to the total outgoing current, which is I1 plus I2. So I3 equals I1 plus I2. Simple as that.
All right, time for our second tool, Kirchhoff's second rule, or the loop rule. Now remember, the first rule was based on the conservation of charge. This one is based on the conservation of energy. It might seem a little more complicated, but trust me, we'll break it down and make it super easy. Okay, so the textbook definition says that the algebraic sum of changes in potential around any closed loop is zero. Now, what does that actually mean? Well, imagine you start at one point in a closed loop. You take a walk all the way around the circuit, passing through all the resistors and cells, and you come back to your starting point. The rule says that the total change in your potential will be zero. It's kind of like going for a trek. You might go up a hill, then down a valley, but if you end up back where you started, your overall change in height is zero, right? It's the exact same idea, but here we are talking about electric potential. But that brings up a really important question, doesn't it? How do we even calculate these changes in potential? And let me tell you, to use this rule correctly, especially in exams, the most, and I mean the most crucial part, is getting the plus and minus signs right. This is where you have to be super careful. So listen up, because these sign conventions are absolutely key. There are just 4 simple rules to remember. 1, if you're moving across a resistor in the same direction as the current, the potential drops, so you write minus IR. 2, if you move against the current, the potential gains, so you write plus IR. 3, when you cross a cell from the negative to the positive terminal, it's a gain, like you're climbing up, so it's plus epsilon. And 4, if you go from positive to negative, it's a drop, so it's minus epsilon. This is where most students make mistakes, so please pay very close attention. Maybe even pause and write these down. All right, enough with the theory, right? Let's actually put these rules into action and solve a part of a circuit. Because remember, practice is the only way you're going to master this. Okay, so let's focus on this closed loop here, AHDCBA. We're going to apply the loop rule to it, we'll trace this loop, and we'll write down the equations step by step using our sign conventions. And you know what? The direction we trace is completely up to us. So for this example, let's go clockwise.
Okay, let's start at point A and move clockwise. First, we go through the 30 ohm resistor. Our path is in the same direction as the current I1, so potential drops. That means we write minus 30 I1. Okay? Next, we continue along, and from D to C, we're moving through the 41 ohm resistor, again in the same direction as the current I3. So another drop. That's minus 41 I3. Finally, we cross the 45 volt cell, going from the negative terminal to the positive. Remember our rule? That's a potential gain, so we write plus 45. And that brings us back to our starting point A, so we can set the whole thing equal to 0. See? It's just a systematic application of those 4 rules we just learned. Okay, now for a very important part. Let's talk about the silent killers in exams. These are the 2 most common mistakes that can, silently kill your marks if you're not super careful. This is so important, bachon. The number 1 mistake is getting the signs wrong. A lot of students just automatically write minus IR for a resistor, but you have to check. If you are moving against the direction of the current, it is a potential gain, so you must write plus IR. And the second mistake is mixing up the signs for the EMF of the cell. Just remember, negative to positive is a gain. You're going up, so it's plus epsilon. Positive to negative is a drop, so minus epsilon. My advice? Always double check your signs before you finish the equation. Okay, so let's quickly summarize. What are the most important things you need to remember about Kirchhoff's rules? Let's do a quick recap. So here are the 4 key takeaways. First, Rule 1, the junction rule, is all about the conservation of charge. Incoming current equals outgoing current. Second, Rule 2, the loop rule, is based on the conservation of energy. The total potential change in a loop is 0. Third, and this is the absolute key to getting correct answers, the sign conventions. You have to practice them. And finally, the application. These rules give you the power to solve pretty much any complex DC circuit you'll see. And why is this all so important? Well, mastering these rules isn't just about solving problems in this chapter. This is the foundation for things you'll learn next. You're going to use these exact same rules to understand very important practical applications, like the Wheatstone Bridge and the meter bridge. So believe me, if you get this right now, it will make your life so much easier later on. So there you have it. You now have the detective's toolkit. With these 2 powerful rules, you're not just a student anymore. You can be a circuit detective. You have the tools to solve any complex circuit mystery that comes your way. All you need to do now is practice. The more you practice, the more confident you will become. So go on, solve those circuits.